Good evening to everyone. No. Okay. Screen sharing ಮಾಡಿದೀನಿ. Okay. So we were saying the single phase motor will continue this. We'll start with the first with the split phase motors. They are also known as a fractional motors because it is used for the small size of motor. Fractional means HP, fractional HP motors. Let's see about this split phase motor. Now, the first one in the split phase motor is resistance. Okay. So first is resistance. Start motor. The other name of this one, resistant start induction motor or induction run motor. It is like that. Okay? Resistance start and induction run motor. So this is also the name. Now we are going to give two windings in this one. So we are going to have a stator. Suppose this is a stator. Okay, this is the stator. And we are going to have the main winding in this. This is the main winding. And there is going to be a auxiliary winding. A resistor is added to this one. And there is a switch. This is a centrifugal switch. That is a centrifugal switch. This is a rotor, a spiral cage rotor. And here we are going to give the supply. So this is the single phase AC. This supply is given. This we say main winding. This one we say start winding or auxiliary winding. Here this is a resistor that is in series with a winding, and this is a switch that is the base. So here the current which is going to flow in this one, this will be the IS. This is going to be the IM. So the total current that is going to flow, that is going to be the R. Okay. Now let's start with this one. First, I will start with the centrifugal switch. Now, centrifugal switch, that is this switch, it is fixed on the rotating shaft. Rotating shaft. So during starting, it is closed. That means this switch is going to be closed during the starting like this. It is going to be like this in this one. So it is being closed when rotor is speed reaches to 80%, 75 to 80, we will write down 75 only. 75% of its NS, that is the synchronous speed, due to centrifugal force it opens. Okay, it is going to open. That means when it is going to open, it disconnects. Disconnects the auxiliary winding. It is not required. Once it is started, thereafter this auxiliary winding is not required, and that's the second name is start winding. And that is why we say this one start winding. So this is how this centrifugal switch that is going to work. Okay, that is the one part. Second part of this one is about the windings. So there are the two windings are there, but both the windings are going to be different in the number of turns and the gauge of the copper wire. So let's see about the start winding. So first I'll write about the start winding, and then I am going to write about the main winding. or I will write down it below only. Okay, start winding. So start winding is going to have number of turns is going to be few. So I will write few turns. Okay, so it is going to have few turns, and second, it is going to have the thin gauge of copper wire. Thin gauge of copper wire winding. Okay, so thin gauge winding we can say. So it is a thin gauge winding. The number of turns is going to be less, and it is having the thin gauge winding. While the main winding, it is going to have just opposite to this one. It is going to have the more turns, and thick gauge, thick gauge winding. So this is going to be different. Now, why we are doing this? We are going to do this so that if the few turns are there, that means we are going to make a low reactance. Means if we say XL, so XL is going to be low for this one. And R resistance. Okay, so resistance it is, or we'll say XLS. S means start winding. Oh, I have written auxiliary winding, so I will be writing auxiliary winding here also. So I will write A here, and RA I am going to write here. So this is going to be high. So XLA, auxiliary winding reactance, is going to be low, whereas the resistance is going to be high. Okay, so this is the characteristics of the auxiliary winding. Main winding in the other similar, not similar, just opposite to this. So more turn, that means the XLM. This is going to be high. This is going to be high. And the resistance, that is the RM. So this is going to be low. Now due to this, what is happening? Why we are going to do this? So what happens? It is going to have the low impedance. So the ZM, that is ZM, that is going to be low. So IM, the current is going to be high. Okay, this is what it is going to happen. ZM, that is the impedance of the circuit, it is going to be low, and IM, that is going to be high. Now here, the ZA, this is going to be high, and that's why the start, this current, it is going to be low. Okay, so IS we are keeping low, whereas IM we are keeping high. And that's the reason this is known as a resistance start and induction run. Resistance starts means this start winding resistance is high. Okay, so it is a resistance start, and then thereafter it is going to run only by the main winding. So that is the induction run, means due to the induction, because this is a spiral cage induction motor, there is going to be the induction run. So this is the main characteristics of this one. Now, so due to these two things, there is a phase difference. Now, if the phasor diagram, if we see of this one, So the current that is going to be there. Now suppose let's see. This is the voltage that will be there, that is the applied voltage. And we know that the IM, so IM, because it is going to have, you can see that XL M is high, reactance is very high, but resistance is low. So the current is going to be high. So you can see this is the current. So this is going to be the IM. Same way, we are going to have the IS. So IS is going to be very small. It is going to be very small, and IM is going to be very large. So this is the IM, that is the very high, and IS is going to be very low. Also, because it is XL is low, so here the phase difference between this and this applied voltage is going to be very less. Whereas lagging of the current is going to be very high in this IM. So it is going to lag. Now the resultant of this one, that is the I, if we find out how much it is going to lag. So again, by the parallelogram, we can find out. So this is going to be the I. Okay, so this is going to be the I. So this is the current that is going to flow in the circuit. So this is the I which is going to flow in the circuit. Okay, and there is going to be a phase difference between this and this, that is going to be the I. So although the current, main current is also going to, resultant current is also going to lag. But what we can see here, that the phase difference between these two also exists. That is the main winding and the auxiliary winding current. Okay, so this is also having a reasonable, not much, but there is a reasonable phase difference. Like we are saying that we require two phases, correct? Yesterday we have seen we require two phases, and both the phases we are applying at the 90 degree, this one. Okay, so this is theoretically we have seen that this phase 1, phase 2 should be at 90 degree. But if you see here, the phases are not at the 90 degree, but reasonably they are having the some differences, you can see from here. So one is applied to this and one is applied to this one. The difference is not much higher. It is going to be some 30 degree to 40 degree. Okay. So this is not much high. So generally this alpha is going to be near about 30 degrees. Okay. So approximately we can say it is going to be 30 degrees. But 30 degree phase difference also, it is going to produce the torque. Okay, produce the torque. Produce the torque means what we have seen. There is going to be the RMF. RMF will be there, and if the RMF is there, there is going to be a torque that is going to be. Okay. So this is how this is going to work. Now, it is going to have a weak RMF. So it is going to produces a weak RMF. Okay, and the starting torque is also going to be less. So starting torque is going to be 1.5 times of FLT. FLT, full load torque. Full load torque. FLT, full load torque. Okay. Then next is when the speed reaches to when the rotor speed reaches to 75% of NS, the centrifugal switch, that is the ACE switch, opens. It is going to open. Now, when it is going to open, only the main winding is going to remain. Okay, so motor operates on main winding. And it will accelerate to n speed. Okay, by main winding. So once it opens, thereafter, only the one winding is there. Okay. Now, how we are going to reverse the rotation of the motor? That is the question that is being asked. How we are going to reverse this? Anyone? How to reverse the direction of the motor? How we are going to reverse the direction of motor? No one is replying. Okay. You can reverse the direction. Okay. So that is the question that comes. How to reverse? To reverse the motor rotation, to reverse the direction of motor rotation. Okay, we need to interchange the connection of one of the winding. Okay, not both the winding. Only one of the winding that need to be changed. So either the running winding or start winding. Now suppose if we are going to change the connection here, we are going to change the connection, then what we are going to do? So here we are going to have the main winding. This was the main winding. And here the connection, this will be given like this, and this connection will be given like this. So before, if the motor was rotating in the clockwise direction, now it is going to rotate in the counterclockwise direction. Okay. Now suppose this was rotating in the clockwise direction. That means this will rotate in the counterclockwise direction. Okay, hope it is clear. So this is how it is going to rotate. So you need to interchange the connection of any one of the winding. Okay, any one of the winding. You need to change that. Now, generally, this one, this centrifugal switch is not going to be used where we have the single phase motors. The application wise, we can use the single phase motor. In the refrigeration systems also, refrigerators, that is the domestic fridge and all, we can use this. So centrifugal switch generally we not centrifugal means this motor is being used, resistance starts. But it is going to, this centrifugal switch is going to create a problem when it opens. When it opens or close also, when it opens, it produces arc. Okay, it is going to produce the arc. Now this arc, which is refrigerant, these refrigerants are there, their properties are going to, their properties will change. Refrigerant properties is going to change. And that's the reason instead of the centrifugal switch, we use the electromagnetic relay. So you will find in the fridge, domestic fridge and all, we generally use the electromagnetic relay. This relay is being used instead of the centrifugal switch. So why it is being used? Let's see about this. So let me make this one. What's the diagram required to make? So EM relay in place of centrifugal switch. So EM relay also can be used instead of the centrifugal switch. So here, if you see the diagram, now this one is a relay. This is the electromagnetic relay. This is a electromagnetic relay. We are going to give the supply. And the contact here, it is open. So relay contact is open. Okay, initially during starting. So during start, it is open. So during starting, when it is open, that means the full current that is going to flow in the main winding. So full current when it is going to flow during the start. So IM is very large because of inverse current. Okay, when this rotor is stand still. So during starting, it is going to be very large. When the current is very large, this EM relay is going to energize. So EM relay energizes. Now this is a relay, it is a current relay. Okay, this is a current relay. So this relay is going to energize. Once it is energized, it is going to make a contact here. So this contact will be made. Now, IS, that is the IS current that starts flowing now. So IS starts flowing. Now, when the IS is going to flow, IM is already present. The motor starts. Motor is going to start. The motor starts. Now IM decreases. As the motor starts, IM start decreasing. IM start decreasing. And when the speed of the motor reaches 75% of NS, IM is drops. IM is drops and relay de-energizes. Relay de-energizes. Okay, relay de-energizes. So the relay contact will open. Relay contact will open. This is what it is going to happen here. Okay, so this is what it is going to happen in this one. So first there is a IM which is going to flow. So this will be the first. Once it is very high, this contact is going to close. Then IS is going to come. Motor is going to start. Once it is going to reach to the 75% of NS, then it is going to drop. So this is going to drop now. The contact opens. Okay, so this is the sequence. So first here, second here, third, fourth, again, this is going to drop, this opens. So like this is the sequence that is going to flow. Let's see about the capacitor start motor. Capacitor start motor. We'll see the capacitor start motor. Okay. Capacitor start motor. Now, this one and the resistance is start motor. It is almost same. Okay, it is going to almost same. Let's see that one, the construction part and everything. Oh, sorry. This one. Okay, this is the same thing, everything remains same. except here we are going to have a capacitor. Instead of the resistor, we are going to have a capacitor added to this. Okay, so there is a capacitor that is added to this. Yeah. And second changes are there in this one, that this capacitor which is being used, this C. Okay. So this C is a electrolytic capacitor. So this one is a electrolytic capacitor. Now start winding here. We start winding. That is going to have a few turns of thick wire. So the thick gauge of wire or thick wire, just I'm writing. And main winding is just opposite. Yeah. So it is going to have the more turn of thin wire. Okay, it is going to have the thin wire and more turns. More turns always it is going to be there from the start line. Only the wire gauge is different now. You can see here, that is what I have written. It was few turns of thin gauge, and here it is more turns of thick gauge. But here turn is same. Here it is few turn, and here it is more turn. But it is a thick wire, and this is the thin wire. The purpose is very different here. We need to make it we need to make it lagging and leading, and that's why we are making it this way. So if we see due to this again, so what happens, we are going to have the IS and IM. So we can just go straight away. Now you know what it is going to be. So just we'll be going here. Still here, the resistance is going to be less. Of course, here the resistance is going to be more. But here we achieve at least we are going to achieve some 70 to 80%. This is going to be the IS, and here this is going to be the IM. So this is the IM we are going to have, and the resultant of this is the I we are going to have. So it is still going to have a good power factor, that is the 5. But if you see between this is the angle. This is almost 80° we are having. Almost 80° angle is there. And that's why it is going to produce a very good torque. So torque which is produced, that is very, very high. High torque is produced in this motor during the start. Again, we are going to use the centrifugal switch. So centrifugal switch we have used here, so it is going to open. So this centrifugal switch, this opens at 75% of NS. and thereafter only main winding makes the rotor to reach to the N speed. So rotor is reaching to N speed only by the main winding. But here, due to this one, we are going to have a very high torque. Okay, so here, due to this angle is more compared to the resistance. So the torque is going to be somewhat 4 times of FLT, full load torque. It is going to be 4 times of the full load torque. The capacitor which is used here, it is almost, it depends, just you can see in the normal ways, it is used near about 250 microfarad. It depends, again I am saying this, how much the value you are going to use, that depends of application, but generally near about this microfarad, 250 microfarad, it is going to be used. Oh, okay. Now there is a permanent split phase motor, that is capacitor. So we will be seeing that one, permanent split capacitor, that is the third. Permanent split capacitor. Okay. So in this the capacitor that is there, that is without centrifugal switch. So centrifugal switch is not having any role in this one. Okay, so here I'll just put this I'll remove. I'll put a capacitor here and just I'm going to connect this. So this is the capacitor that is being used. This capacitor is of low value, and generally it is 2.5 to 3.5 microfarad. Okay, this is the value that is going to be used. And this is a paper capacitor. This is generally it is a continuous running, so electrolytic type cannot be used. And this capacitor is a paper capacitor. Okay, so this is a paper capacitor. Rest working is everything is same. Okay, so it is having no starting switch. That is the one thing. Of course, here the starting torque that is not much. It is having a very low starting torque, this motor. So this motor is going to suffer with the low starting torque. We have the advantage that it is no centrifugal switch. So this is the advantages. Okay, so this is a demerit. This is a demerit basically. And this is the merit. So this is the demerit, this is the merit it is having. Now, Let's see about the direction, where how to change the direction of this motor. For changing the direction of this motor, here we are going to make this motor that will be running, and we need to really change this one. So I will make the another diagram. So how to reverse the direction. If this motor is there, the direction reversing is very easy, because we need to no need to change the connection. Okay, we need to change only the capacitance polarity, and it will be done. Okay, so let's see how it is going to be. So suppose this is a rotor. This is a rotor. Okay, and we are going to have the winding here. And we are going to keep this capacitor here, like this. Then we are going to give the connection. So if we give the connection, we need to have two wire coming out of this, and we need to have a switch. This is for the forward, and this is for the reverse. And we need to give the supply single phase AC. Like this. So in the forward direction, what it is going to happen, the forward direction, when it is there, the current that is going from here, the current, this is the IM that will flow through this. Okay, like this, and this is the IS, that is the start current that is going to flow, or auxiliary current you can say. But when the switch is changed to this position, when the switch is in this position, here, this one, now this one is going to become the IN. This is the main winding, it will become. And this is going to become the IS. So this is going to work in the reverse. So this is the reverse. And when the in the forward, this is going to be in the forward. Now why I am written IM here also, IM here also? Because number of turns and gauge of fire is same in both windings. Okay, so this is the one note you can have. So both the winding is having the same. Only the capacitor that is going to come either with this or either with this. So when in the forward bias, this becomes a main winding and this becomes a start winding. But here we can't say start winding, there is another winding, auxiliary winding. Okay, so it is auxiliary winding. Now, here, next when we are going to make it reverse, this becomes the main winding and this becomes the auxiliary winding. So likewise, we are going to have the two currents continuously. It is going to flow. Now let's see about the next winding. Copy this. Okay. Then we are going to have the capacitor start and capacitor run. Capacitor start and capacitor run. Now in this, we are going to have a capacitor, but with parallel to this, one more capacitor we are going to have. Okay, so one more capacitor that is being added to this one. And this capacitor we say start capacitor, and this capacitor we say run capacitor or permanent capacitor. So just I will write it CR and CS. CS means this is a start capacitor, and CR, this is a run capacitor. It's permanently connected like this. So CS is always connected with this switch, centrifugal switch. Okay. Rest everything is going to be same, only except that during starting, both capacitors are in parallel. Okay, this is the symbol of parallel. Both are in parallel. Or just as the parallel, otherwise you get confused. Both are parallel. Okay, both capacitors are parallel. If both capacitors are parallel, then capacitance is going to decrease or increase. What will happen? Capacitor increases or decreases?
Increases.
Yeah, that's correct. Okay, so capacitance is going to increase. So if it is going to increase, it is going to provide a very good torque. Okay, so starting torque is going to be very high because the capacitance is high during this period. So it is going to have a good starting torque due to this. Okay, so almost twice of the FLT it is going to have. Twice of FLT, 2 times of full load torque. It is going to provide the starting torque. So it is a good torque. It is not so good as we have the capacitor start, but at least it is going to have a good torque. Now the CS which is being used here, this CS, this is a electrolytic type. Again, okay, CS is electrolytic type. And CR, which is there, it is of the paper type. So there is the electrolytic capacitor and this is the paper capacitor. Now, this one, This run capacitor, the value is around 36 microfarad, okay, of this. Whereas this one is going to be near about 120 to 150 microfarad. So this is the electrolytic capacitors, that is the value, and this is the paper capacitor, that is going to be the value. So 36 microfarad, that is going to be there. So again, same thing is going to happen once it is going to reach to the 75% of NS, then the AS will open, the switch will open, and it will be run only by the CR, permanent capacitor. This is the CR capacitor. So runs with CR. Okay, this is going to run only with the CR. So this is a paper, but this is a oil filled paper. Oil filled paper. Remember? Because it is going to run continuously for a long period. And that's why this capacitor is being used. This is for a short time, only during the starting. That's why the electrolytic paper is used. When we are going to connect continuously the capacitor, we cannot use the electrolytic. There is a limitation to use on that. So generally, the auxiliary current during starting, it is going to be phase difference is going to be more than 90 degrees because both the capacitor are in circuit. And once it is disconnected, okay, in that case, only one capacitor is there and it will be around equal to the 90 degrees. Okay. So that is the torque, how it is going to generate. Once it opens, then only the run capacitor that will be connected permanently. So you can take a break, then we'll start with the sided pole motor. Okay. We'll start with the sided pole motor. Okay, next we'll see about the shaded pole motor. Okay, shaded pole motor, how it works.
Sir, I have one question.
Yeah, tell me.
Sir, in case of a capacitor start motor, like on ships we don't have any neutral, we have two-phase supply. So
Yeah.
like this rule applies to there also, or like we can change the phase sequence in single phase, like we have two phase in concepts. So if we change the phase sequence, then motor can be reversed.
Ships, we have the two phases only. Okay.
Yes, sir.
Generally, we are going to have the two phases. But two phases, it doesn't mean. Okay. What is two phases basically? See, you are going to tap the output like this. So this is the RST. And suppose this is a 220 volt. Yeah. Domestic supply generally we have this much. Okay, so you are going to tap the from this one. Okay. So here you are basically going to have these two phases that is going to alternate. Okay, so if you because one is if you are taking the reference, if you are going to take one as a reference, okay, so other one is continuously changing. So basically, with this one, it is a single phase only. Okay, in this also, if you take the two output, it is not like that you are having the two phases supply. It is a single phase supply only. Are you getting me?
Yes, sir.
Yeah. So it is going to be same. So what we need to have this capacitance. Otherwise, onboard ships we do not require the capacitance only. Why we require this resistance and capacitance? Okay, it doesn't require. Now reversing the motor is basically the magnetic field what we are going to give. So we are going to change that magnetic field. Yes, what we can do here, that is your question is, if we change like from S and T I have taken, if I am going to take from the R and S, okay, it should reverse or not. It may not reverse. It is not going to reverse because you have to reverse the magnetic field. So when we are reversing, like when we are reversing here, the connection, basically we are reversing the magnetic field, and due to that, our RMF, that is changing. If the RMF is able to change, then only we can reverse the motor. I hope it is clear. Okay.
Yes, sir.
Okay. Now next is the sided pole. Sided pole motor. Sided pole motor, we are going to have in this one. Let's see what is this. Okay, we are going to have this way. Okay, if I can reverse this one, copy. No, not able to do. Okay. Let me make only. And this side also we are going to have the similar way. Now we are going to create a, we are going to give a supply here. So we are going to give to this winding like this. Okay, and we are going to give to this winding. Okay, so this is a single phase AC supply that is given here and here. Now suppose this is going to make a north pole and this is going to make a south pole. Okay, suppose just will be taking as a. Now this one here, it is going to have a thick copper wire. It is going to have a thick copper wire. And here also it is going to have a thick copper wire. So this construction wise, this is going to have a thick copper wire. Copper, Cu, ring. It is a ring that is fixed in this one. And this is also same. So where we are going to have the thick ring, this is known as a shaded portion. And this portion here, this portion is known as a unshaded portion. Unshaded portion. Then we are going to have the rotor. Okay, so this is the squirrel cage rotor only in between. Now we will try to analyze of only one pole. Next side also it is going to happen in the same way. This type of poles are known as a salient pole. Salient pole. Okay. So this all are a salient pole. Now how it is working? Let's see about this one. Now when we are going to have the winding, again I need to make, so I will be making here. So just I am making like this for a better explanation. Okay, I'm going to make in this way, and we are going to have a shaded portion here. This is the shaded portion. And okay, we are going to have the winding. Now, this is going to work during the means AC supply that is given to this. And the AC supply which is given this is the AC supply. First half we are going to see in this one. So it is rising from 0 to A. A to B, it is going to remain constant, and again from B to C, it is falling down. Okay, it is going to fall down. So if you see during this period, it is rising. From here to here, it is rising. So if the rate of rise is there of the current, if the rate of rise is there of the current, that is going to create a varying magnetic field. So if the varying magnetic field is there, then this particular ring is going to have the EMF induced in it. Why? Because 0 to A, there is a rate of change. Rate of change of magnetic flux. So the EMF is going to induce in this one. Now, if the EMF is going to induce and it is a closed ring, so induced current will be there. Now, induced current will flow in such a way. Suppose this is a north, the end pole, it is making, suppose this current is making this one end pole. This also supposed to make the end pole. Okay, so if it is going to make end pole this side, and this side is pole. So this side it is going to be the end pole. Then it is going to, then only it is going to oppose the main flux. So main flux, this is the main flux that is being opposed. So it is induced current in such a way that it's supposed to oppose the main flux. So because this induced current has to have its own flux, and this flux will oppose the main flux. Now suppose the direction we are showing here, this is the direction of the current that is going to flow. Okay, this is the direction of the current that is going to flow. So in that way, it is going to have its own flux which is going to oppose the main flux. If it is going to oppose, in that case, whatever the magnetic flux are there, these flux are there, they are going to shift in one side. So that is going to get strengthened. So this side it is going to become strengthened, and this side it is just going to become a weak. So this side it is going to be very less, and this side it is going to be more. And the MMF, if you see, this is going to be the center of that, means of the magnetic force. So this is going to be the MMF. So we will just say here D. So this is the point it is shifted. Why it is happening? It is happening because there is a rate of rise, and this is the ring, it is a closed ring. So it is going to have the flux, and which is going to oppose the main flux. Okay. Now, during the A to B, what will happen? During the A to B, what will happen? Let's see now. So this is the when during the current is rising from 0 to A. Now next is when it is during A to B, what is happening? What is going to happen? So during A to B, during A to B, when the current is at this from point A to point B. Now if you see, this is almost constant. So if it is constant, here in the ring, nothing will happen. Nothing means no EMF. Because no varying field, so no EMF. If no EMF, no current, no induced current. If no induced current, then there is going to be no opposition. So the magnetic flux which are there, that will be distributed equally. That is going to be distributed equally. Equally means it will be distributed equally in such a way that MMF will come at the center. Okay, so it is going to be equally distributed. It is going to be same this side. Like suppose I am showing with the 4. This side also it is going to be the 4. Equally it is going to be distributed. And there is not going to be any current. I have shown the current. Current is not there. Current will not be there. Okay. Current is not there. And it is equally distributed. So the MMF or central, it will come to the center. Okay, so pole which was there before means at the D point, now it has shifted to the E point. You can see before it was here, now it is shifted to the E. Now let's see when there is a fall from B to C, what it is going to happen. So during B to C, now here it is falling from B to C. Again, there is a rate of change. So there is a rate of change, again there is a rate of change. And rate of change is there in such a way. So again it is going to produce its own flux. Okay, so during B to C, when the current is changing, now in the ring, because it is a closed one, there is going to be the induced EMF, so induced current flows in it. When the induced current is going to flow, it will flow in such a way, the direction will change now, it will flow in such a way that it opposes the main flux. Now it is going to oppose in such a way so that what will happen in the sided portion, more magnetic line will shift, or it is going to will get strengthened. We can say it is getting strengthened. Will be strengthened, and this side it is going to weaken them. So this side it is going to become very weak, like this, and this side it is going to become, concentration is going to increase. This side it is going to increase the concentration, and this side it is going to decrease. So your MMF, the point that is going to shift around this point. So before it was D here, then it was the E equal, then it is the F here. So you can see it is shifting from like this, continuously it is shifting. This shift is nothing but it is going to provide from here to here a RMF. Although it is a small arc just within the salient pole, but this is an RMF. This shifting is in is a RMF. It is a RMF. Let's see here. Because it is a salient pole and it is generally covered up to here. Up to here, this pole will be covering half of this one. Okay, this salient pole is made in such a way that it is going to cover. It is shown, I have shown up to here only, but it will be generally covered up to here. Okay, or sometimes it is made in such a way that this entire parts are being covered. Okay, how it is being covered, you can just I'll put it here, you can see. In this way also it is made. So one side it is going to be the sided pole motors. Now you see here, this is how the actual motor is this way. Okay, this is the actual motor, it is. So this side it is one pole and this side it is going to be other pole and this is the copper sided ring. So almost full of this one is, it is covering. That means if the RMF is there, okay, first it will be here somewhere and it is going to shift from here to here. So it is going to make a good arc, if you see. So this RMF will be there from here to here. This is the RMF. Similar way, from here, this S side also it is shifting from here to here. Like this, it is the N pole, S pole is also having the same down below. Okay, so this is the entire pole, means N and S. So N and S will make here and it will shift from here to here. So this is the N and S. This is the final N prime and S prime, you can say it will shift here. So this shifting from here to here, that gives a generation of the rotating magnetic field. And this rotating magnetic field, although it is a very small arc, it is not a full 360 degree, it is rotating. But it can give a starting torque. It can have a starting torque. This starting torque is very, very small. Okay. So this starting torque is a low starting torque it is going to produce. But it will produce the starting torque. This starting torque is 40 to 50% of FLT. Okay, if it is 40 to 50% of the full load torque, means it is less only, it is less, but it is going to be, the torque is going to be there. So the application is same way application is there. It cannot drive the big loads or cannot start a big loads. So it is required a very light load. So generally you will find in the cabinet cooling fans are being used. This is the application. So in the CPU, the cabinet fan or any enclosures, like we have the electric enclosure, starter panel and all, where the cooling is required, this fan is being used. Why it is being used, that is the one more reason. It is very silent fan. Silent fan, okay, not silent. Now it is a silent. This fan is very silent. It is not having any, it does not produce any noise. Okay, so it is being used for these purposes. So noise is very less, it is a silent fan, and cabinet cooling fans it is being used because it is having a very light load. So the applications are there in this way. We are going to use this one. So this is the sided pole motor. Now we will see about the universal motor. Okay, so let's see the universal motor and we can conclude for today. So next is the universal motor. Universal motor. This universal motor, if you see, it is this motor runs on AC as well as DC, both, okay, as well as DC. In both, it is going to run. Both the current, it is going to run. Now, it is going to have the armature winding. And it is also having the field winding. So field winding directly we give the supply and armature winding. So with this, both the windings are connected in series. Okay, they are connected in series. Now armature winding is given supply through commutators and brushes. Okay, so commutator and brushes that is used in the armature winding. From field to armature, they are connected in series. Okay. So if you see this motor, universal motor, is theoretically so as per theory, theoretically, if you see this one as per theory, it is same as DC series motor. It is same as DC series motor. But we can give the AC in this one also. Now, DC series motor, as we know, it is going to have without load, it produces a very high torque. Not very high torque. It produces dangerously high speed. Dangerously high speed without load. Okay. So it is also having a very high torque. So this is the one cause of concern, this one. And second, it develops very high torque. Now it is running at very dangerously high speed. That's why always it should be operated with load. Okay, with load. It should be always operated with load. That is very, very important. It should not be run without load. Now, let's see how it is going to work. So everybody might have seen the drill, portable drill machine. Okay, it is same. Or you might have seen the mixer and grinder in kitchen. It is same. These all are the universal motor. Universal motor. It is going to work in both AC as well as DC. Okay. So this motor, this universal motor, it is having the characteristics that this motor develops unidirectional torque always. Whatever the supply you give, regardless of AC or DC, whatever the supply you give, it is always going to have the same unidirectional torque. In the same direction, the torque is going to be there. Okay, so this is a unique thing. It is happening. Now, why it is going to give the unidirectional torque? Because the polarity changes. Polarity changes, or we can say the alternating current, AC. Same thing, the polarities changes in armature and field winding. Same thing. So the direction of the torque cannot be changed. So it is not changing only. Okay, so direction is not going to be changed. How it is going to work? Let's see. Okay. Now you can see here, suppose we have given the polarity here, the plus. At this point, we have given the plus at this one. And here we have given the minus. So current is going to flow. Here it is going to be N, and this side it is going to be S. So this is the direction of the flux, magnetic line of flux. This is the direction we are going. Okay. So just I'll represent only with the one line. So this is the direction we are going to have. And now the supply that is going to come to the this rotor, and the direction is shown with the dot. You can see here the dots are there in this half of the winding. We have the dots. And half of the winding, we are going to have the cross. Okay, so this is dot and cross we are going to have. So now the torque is being produced in this one. This is the rotor which is going to have the torque. Okay. So that rotation of this, if you can see here, this is the counterclockwise. So this is the counterclockwise, the rotation is there. Now the torque which is being produced, you can again use the this one, the current, because here we are having the current direction is given and the field direction is given. So you can use the Fleming's left hand rule and you can find out the torque. So if you see for this one here, the direction of the torque will be in this way here. This is the force of the, this is the direction of the torque. And here if you see, because current which is flowing in the opposite direction, the torque is going to be in this way. Okay, this is the force. Yeah. For all this one is going to happen the same way. So it is going to rotate in the counterclockwise. Now let's see here. Now when the polarity change, you can see here this is the negative and this is going to be the positive. So your field now that is going to change from here to here. So this is the direction of the field. This side again, because before it was the dot, now it is a cross here. This is a cross. And this side we are going to have the dots. So the direction, again, if the dot is there, but direction of the this field that has changed. Okay. And direction is changed. That's why here the force that is going to be again downwards. This side the force will be there. You can use your left hand, Fleming's left hand rule. Just use everyone. So you come to me. And this is going to be the direction of the current, and the force is going to be this way. This is the force that is going to. So whatever the polarity AC or DC, or even we are changing the polarity, like AC always it is going to change, positive half cycle then negative half cycle, but direction is going to be same. Unidirectional torque will be there always. So this is a universal motor which is going to work on the AC or DC, and the direction is going to be changed for this one. We have a switch, you know about that, in drilling machine you might have seen. And that switch which is going to change one of the winding. So one of the winding, if it is being changed, then only we are able to reverse this. So it can be reversed only by the changing the winding connection, as we have seen for the other motors, single phase motor also, they are also unidirectional. Okay, it is always whatever the polarity, AC or DC, it is always going to work on the, AC, positive half cycle or reversing negative half cycle. it is always going to rotate in the same direction. Okay. So here also you can see this is a torque versus speed. But here you can see this is the suppose counterclockwise it is rotating, and here the direction is changed. This is the current. The connection is changed from here to here. Okay, so this one before it was this was the plus here you can say, and this was the minus. Now here this is the plus and this is the minus. So this connection has been changed, so the rotation is also changed. Okay. So this is how this motor works. Any doubt up to here to anyone or anything else do you want to ask me? Okay, so that's it for this motor. We will see now the three-phase motor. Okay. So three-phase motor, we are going to have the three-phase winding here. So we are going to have a three-phase winding. This and these windings are displaced at 120 degree. These windings are displaced at 120 degree to each other. So their MMF, if you see, this is also going to have it the 120 degrees. So you can see from here to here, it is having 120 degree. From here to here, it is going to have 120 degree, and from here to here, 120 degree. So suppose this we can say, this is the supply what we are going to give here. So this we are going to give the phase 1, and here we are going to give the phase 2, and here what we are going to give the phase 3. Now this phase 1, suppose we are going to give supply, so which is going to produce the flux. So this produced flux will be again sine omega t. So this is going to produce, because the current current what we are going to give. Let's see about the current first, then we'll come to the flux. Okay. Current which is given, so it is going to be the In sine omega t. Here, this is the second phase of the current. So this is going to be given. Im is going to be same sine omega t minus 120 degree, because this is the clockwise direction, so minus 120. And here, this is the I3. So this is the Im sine omega t minus 240 degrees. This can be written, or this I3 also can be written Im sine omega t plus 120 degree. It can be written if you see from this side. But generally we keep only one side, okay, for calculation purpose. So it is always good to have only one side. Okay. Now, it is going to produce the RMF. Okay, it is RMF, rotating magnetic flux. If we are going to give the supply to this one, it is going to produce the RMF. So it will produce the RMF which is going to rotate, because three phase also it is three phase supply. Two phase supply, if it is going to produce, of course the three phase supply is also going to produce the RMF. Because this is going to have the flux. So this flux we can say, so this is going to be the maximum sine omega t. This flux is also going to be of this one, phi m sine omega t minus 120 degree. And this flux which is going to be produced, this is the phi m sine omega t minus 240 degree. So these all are the instantaneous phase which are having the amplitude that is the phi m. Now we can see in the different instant when the WT is going to be 0. At point 0, we can have a instant in the different. So we can find, if we see this one, now you see at this instant, now just I will put here the supply which is given. This is the supply we are giving to this. Now this is the instant. Here it is a RYB it is written, but we can give the 1, 2, and 3 what we have seen here. Phi 1, phi 2, phi 3. So at this instant, this one is having the value here, and this is the value of the. So this one is the phase 1, we can say. Okay. And this one is the phase 2 flux. Sorry, flux 1, flux 2, and this is the flux 3. So at this instant, we can find out the exact value. So here, the phi 1 is going to be 0 because phi m sine omega t is going to be 0. Then phi 2, we can again have phi m sine 0 minus 120. So minus 120, that is going to come root 3 by 2 phi m. This will be the value. And phi 3, the value of this one is going to be root 3 by 2 phi m. That means if we are going to see the resultant of these two, we are going to have a flux that is going to be this side and one flux that is going to be this side. Why this side? Because this is the negative. So this is going to have the negative root 3 by 2. And this is going to be root 3 by 2. This is the opposite of that one, negative side. So this is going to give a resultant of these two. And we are going to have a flux. And this is going to be of 3 by 2 phi m. 3 by 2 phi m. So this will be the amplitude of the resultant flux. So resultant flux is going to be the 3 by 2 phi m. And this is going to always remain constant. This we have seen at the instant when the omega t is going to be 0. We have seen at this point. This side we are having the omega t. Okay, and this side we are going to have the plus phi m, and this side the minus phi m. Now let's see at this instant. At this instant, 1. If you see at the instant of 1, okay, so at the 1, omega t is almost 30 degree. At that instant, it is 30 degree. Okay, you can see again from here to here shifting is almost 30 degree. And this is the 60 degree and this is the 90 degree. Okay, so here it is 60 degree, 30 degree, sorry. Now sine 30 degree, we know that again phi 1, that is going to be sine 30 degree. So it can have 1.5 phi m. Phi 2, that is going to be 30 minus 120, so minus 90. So minus 90, sine minus 90 is going to be minus phi m. That is about the phi 2. Here, this phi 2 at this point is the maximum. So phi m, maximum, phi m will be there. And third one, this one, again 30 minus 240, so minus 210. So it is going to come again the half of phi m. Both are same. Phi 1 and phi 3. If you see here also in the graph, both are same. So it is going to be this way. And if you take out the resultant again, resultant of this, so phi r is going to be 3 by 2 phi m. Okay, it is going to be this. If you want to see the phasor diagram of this one, okay, you can have in this way. This is the phi r, this is going to be phase 1, and this is going to be the phase 2, which is going to have the half of phi m, and this is also half of phi m, and we are going to have one more phase. This is the phase we are having. This is the phase 3, and phase 3 is nothing but minus phi m. I think I have written wrong. This is the 2 and this is the 3. Okay. So the resultant, if you want to find out, first of all, we need to find out the resultant of this. So we can do the parallelogram of this one. Okay, so this is going to be the resultant. This one, this is going to be the resultant of this, approximately half. And again, you can add the half in this one. So this is the total resultant, and this is going to be the QR. So you can see the QR. QR is going to be equal to 3 by 2 of the IF. So amplitude doesn't change. Here also you can see this was the QR, which is having 3 by 2 by of IF. Here also it is going to be 3 by 2 of IF. So this was the resultant of these two. Then you can add this one and this one. So it is going to be 3 by 2 pi. So amplitude is always going to remain. Only the direction that has changed now. Of this vector diagram, it was pointing downwards. Now it has been shifted from this one to this side. Continuously it is shifting. Continuously it is shifting in this direction. So clockwise direction it is shifting. And it is shifted by clockwise direction by 30 degrees. At this instant it has shifted, it is continuously shifting and it is shifted at 30 degrees. Same way, if you can go for the stand 2, stand 3, stand 4, you will find that this vector is shifting continuously. This resultant vector is shifting continuously and having a constant magnitude. It is continuously shifting and it is going to have a constant magnitude. So what we can conclude is, hence, we conclude that first of all, we can say the resultant flux, that is the phi r, is of constant value (3 by 2 pi m). Okay, is always a constant value. And second, the phi r rotates around the stator at ns speed that is given by 120 f by p rpm. It is always going to rotate at the synchronous speed, that is the rpm. Okay, so hope you understood about this one. So this is how this RMF, when the three-phase supply is given, this is how the RMF is being produced. Tomorrow we'll see about the torque and all, because that question has come. How does the rotor rotates and how the torque is being set up, then slip. And there is a starting torque, maximum starting torque, and the maximum running starting torque. We'll see, because this has come in your exam, oral exam also they have asked you to see tomorrow. Okay, so thank you very much, and good night to everyone.
Thank you, sir.